Hello and welcome to Toddcast number 8. I'm going to deal with boiling points and melting points, and then the physical properties that those are, I guess, the molecular basis for those physical properties. And it's going to be, I guess, mostly OChem, but there's going to be a little bit of bio required to get this. So hopefully, I'm counting on the fact you have a little bit of your GChem background, that OChem, you've gone through the first 7 Toddcasts and have a good foundation, and then you've actually have interacted with some bioinformation. If all that works out, then this should be relatively straightforward and easy. So boiling point, in GChem you learn boiling point is the temperature at which the vapor pressure equals atmospheric pressure. And they define it that way so that when you go to different elevations or different conditions, you can modify the boiling point by reducing or increasing the atmospheric pressure so that the target vapor pressure changes. We're not going to define it that way in OChem. We're going to define it, or at least I'm going to define it, as the highest temperature at which a liquid may still be present. Meaning once you're above the boiling point, it's converted to a gas. But the boiling point, highest temperature, you still get a liquid. So we're going to define it as a temperature where all the liquid has to convert to gas. Okay, so if we think about what that means the particles that are interacting, their intermolecular forces holding together, intermolecular forces have to break, not intra, not bonds. There are no covalent bonds being broken, but any sort of interactions between molecules. And to revisit, the 3 we're going to worry about will be H bonding, polarity, so polar-polar, dipole interactions, and then London dispersion forces. Those are going to be 3 we're going to worry about. So the reasoning behind the boiling point is going to come down to 2 factors. Intermolecular forces, which we just named there, the 3, and then molecular mass. Heavier molecules require more energy to vaporize because you actually have to lift the molecule away from the solution and let it freely move around in space. You have to give it kinetic energy. Larger molecules require a greater amount of kinetic energy because if it's 1/2 mv squared, to move at the same speed, you have a bigger m. So in general, molecular mass and intermolecular forces. It's essentially impossible, maybe not impossible, very, very difficult to make a prediction which one is more significant. There are very large molecules that have absolutely weak intermolecular forces, but still have a high boiling point. And there's really small molecules like water have a really low molecular mass, but those high molecular forces make it a very high boiling point. So we have to treat them independently, and one factor isn't necessarily going to influence the other. Okay. In general, stronger forces equate to a higher boiling point, and then heavier mass relates to a higher boiling point. So both of these factors are going to come into play. So I'm going to just start off with an example. So this compound, we use it in lab a lot. I've repeatedly brought this up in some of the previous podcasts, but I want to just do the calculation of mass real quick. Carbon, 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 3 carbons at 12 each, 36, plus 3 and 3, 6 H's at 1 each, so 36 and 6, 42, plus 16 for carbon is going to be 58 grams per mole. Okay. And I need to point out that it has a delta plus and a delta minus because of Funkelbrich. Funkelbrich, where O is more electronegative than C. So O is going to take the electron density, make delta minus delta plus. So it is both polar and it has a mass of 58 grams per mole. Going to compare that to another 2 carbon species known as ethanol. So acetone, and actually I lied, it is only a 2 carbon species with an O. So it's going to be lighter. So let me just do the math. 2 carbons, 24, plus 6 H's, so 6, plus 16 equals 46 grams per mole. But it has an H bonded to an O. So it has H bonding possible between molecules of ethanol. Acetone has polar interactions. So from what we learned, hydrogen bonding, if you have hydrogen bonding, you are also polar. So this has polar and hydrogen bonding. This has just polar interactions. So we describe this as polar, whereas this is an H bonding species. Stronger intermolecular forces, even though it's lighter, the stronger forces, hard to predict, but the masses aren't that much different. So I'm going to lean towards the fact that intermolecular forces, H bonding is so much stronger than polar, it should have higher boiling point. So again, molecular mass 58.1, 58 is what we said, boiling point 56, lower molecular mass, but it ends up and has a boiling point of 78, higher. So even though it's lighter, and in theory should take less energy because it's lighter, it takes more energy because it has a stronger force between neighboring molecules. This is what you're going to have to be able to do when you look at molecules. And you'll start seeing patterns, and it won't be hard after a while. But it's one of those topics that's just very, very challenging in the beginning. Okay, so let's consider some other boiling point scenarios. You, again, have to recognize what these structures are. So here and here represent carbons. That's a carbon. So this would be H3C, CH2, CH, timeout, C double bonded to O, CH3. There's a carbon in the middle, this carbon in the middle. So this one is C4, H8O, C3, H6O, C2, H4O. All three have polar functional groups, double bond to O, and all three, excuse me, have all their H's connected to carbon, all their H's connected to carbon, all their H's connected to carbons, meaning no F. There is no N, O, or F in the molecule for the H to be connected to. So therefore, there is no H bonding. So in this case, all three have polar interactions, equal polar interactions, but they have different molecular weights. So 48 plus 8 plus 16, sorry, that didn't come out right. So 56, 66, 72, 36 plus 6 plus 16. We did that one earlier, 58. 24 plus 6, 16 is 46. Okay, so I just realized I did this wrong. My apologies. It is plus 4. I was stuck in the past, 44. So this is 14 higher and 14 higher, which makes sense. It's inserting a CH2 group. This one took away CH2 group if you think about it that way. So heavier mass, same molecular forces, higher mass should be a higher boiling point. Sure enough. Butanone, around 80. Acetone, we had as 56 before. Ethanol, around 20. So the extra 14 made it go up by about 30-ish and about 30-ish. So this is actually like 24, this is 36, but in that ballpark. As it gets heavier, boiling point goes up. So two factors. Heavier makes a higher boiling point, stronger intermolecular forces make a higher boiling point. I'm gonna talk about a weird third factor, and that is branching, or the nature of the three-dimensional structure. So again, this represents a carbon, 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 5 carbons with 3 H's, 2 H's, 2 H's, 2 H's, 2 H's. So I'm going to draw those in real quick. H's, H, H, sorry. H, 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 H. So everywhere I have a blue circle, that represents a carbon, and OH. So in each case, I have 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, and H's. The difference is, a notable difference in this one, The OH, the group that can hydrogen bond, is at the end. Over here, it's perfectly in the middle, and this one is sort of off-centered. So this is something where you have to start visualizing three-dimensional molecules to fully comprehend. There are two factors, molecular mass and intermolecular forces. So in this case, they all have the formula C5H12O, which means every one of them is 60 plus 12 plus 16 for 88 grams per mole. So all differences come down to intermolecular forces. Intermolecular forces, H bonding, H bonding, H bonding. So in theory, they have the same intermolecular forces and they have the same mass. They should have the same boiling point. Well, the tone in my voice hopefully indicates that isn't quite the case. Intermolecular forces are based on the type, hydrogen bonding, hydrogen bonding, hydrogen bonding, but also how strong it is. If the OH is down here by itself and the rest of it's out of the way, it's free to combine with another molecule pretty easily. So another one of these molecules can come in and they can interact because they're right next to each other. But if you're in the middle over here and you try to get another one in the way, then these two ends start to interact a little bit. They start bumping into each other. So positioning of the OH, where it's near the end, and we mentioned real briefly in a different earlier podcast, this is known as a primary carbon or a terminal carbon. It's at the end and it has only one carbon attached to it. These are secondary carbons. Secondary carbons are going to be more crowded because they have more other carbons around them. That's a 2 and a degree that somehow we do it that way. It's not a 20 or a 10. So primary carbon, secondary carbon, secondary carbon. Secondary carbons are more crowded. They have more large carbon-based groups around them. So they can't pack together as tightly. So the better you can pack, the better you can have intermolecular forces. So this actually has the strongest intermolecular forces. These two, pretty close. Don't know which is going to be better, so we'll see how the numbers go. 138, sure enough, that's higher. These two are really close, but when it's a little bit closer to the end, it's just a little bit better. So that's such a small difference that's really close, but this one, notably different. Okay, want to emphasize nomenclature. Bute is 4 carbons, anone. Acetone's a common name, so we just memorize. So we'll go into anything that has that. A CH3 with carbonyl begins with the word ace, acetone, acetaldehyde, acetyl-CoA if you've taken bio, but just a note of interest. So acetyl with the CH3 is acetone, and then ethanol, 2 carbons. Nomenclature-wise, 1, 2, 3, 4, 5 carbons. Pent is 5. So pent, anol, because it's an alcohol. Pent, 5 carbons, anol, pent, anol. Nomenclature, we won't do much nomenclature in class as an entity in itself. It's going to be pieces along the way here and there. But an OH on carbon number 1 of the 5 carbon chain is 1 pentanol. OH on carbon number 2 of the 1, 2, 3, 4, 5 carbon chain is 2 pentanol, and OH on the 1, 2, 3 third carbon is 3 pentanol. So nomenclature, they're all pent, 5 carbons, anol because they're alcohol. It's just the 1, 2, and 3 represent where the OH is positioned. When it's at the end, it's less hindered, so it can interact hydrogen bond, if you will, with other alcohols more easily, which resulted in a higher boiling point. So your logic has to consider intermolecular forces, how strong the forces are, and how well the molecules can get close enough together to have those forces, and then molecular mass. So combining all of it, we have 3 carbons in a primary, 3 carbons secondary, 2 carbons primary, 1 carbon. So we have these two being equal mass but heavier, but primary and secondary, lighter and lighter. So the mass last time for the ketone was about 30 grams or 30 degrees for every extra 14 grams. So it isn't an exact science, but I'm going to say if you estimate about 1.5 to 2.5 degrees per gram increase in mass, it's not too terribly far-fetched. It's not perfect, but it's a decent guess. So these two will be close. This is 14 lighter, so it's going to be around 28 lower, 14 lighter, so around 28 lower. I don't know if it's going to be exactly that, but we're going to say in that ballpark. And then, because this is near the end, it can form a hydrogen bond better than this one. So primary is going to be slightly easier at forming H bonds than secondary, so it's going to have stronger forces and a slightly higher boiling point. So it ends up, this is higher by about 15 degrees. So positioning, just like we saw last time, 137 versus 119, that was 18 degrees difference. This is 15. So it's not a perfect science, but it makes sense. And then mass-wise, so the terminal, 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 so comparing primary, 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 it goes from 97 to 78. That's only 21. So that's about 1.5 degrees per gram. And this one only divided by 14, so only about a degree per gram. So clearly this method of estimating it isn't working too well, but it's in the ballpark. And I use the number 21. This actually differs, by the way, by only 18.6, but I use 21 because I want to divide it by 14 to make about 1.5. I wanted my number to be clean, but the trend is fine. The exact numbers, they don't work well. So take home message from this. If you get a question, it's highly unlikely that it will be told to predict the boiling point because it's hard to do, but explain the trend in the boiling points, absolutely important. So 3 factors: molecular weight, heavier things have higher boiling points, and intermolecular forces, the type of forces, hydrogen bonding, hydrogen bonding, hydrogen bonding, hydrogen bonding, and then the ability to form those forces, the shape and structure of the molecule. So how hindered it is from having those interactions. So intermolecular forces, 2 factors: how strong is the force, and 2 is the molecule shaped in a way where it can have those interactions. Okay, so this is a little bit different concept. This is OH on 1, OH on 1, OH on 1, but now instead of a long chain, it's a long chain with what they know, a branch coming off. So a branch is coming off further away from the OH, a little bit closer to the OH. Just like before, if it's all isolated by itself, it's going to be able to interact easily. So it's here, but this little group here, just that little bit extra, makes it a little more crowded, not much. But as that group gets closer and closer, it becomes more hindering. So just like when it was secondary, this is primary, but secondary would have the methyl there, and it brought down a lot. So this had the strongest intermolecular forces, so that it had the highest boiling point. The one that was secondary brought the intermolecular forces down a lot, so the boiling point went down. Should see the same trend here. But notice it's not nearly as significant as it was going from primary to secondary. So hopefully this makes some sense as you go through it. Don't get overwhelmed. Don't memorize boiling points, but take the time when you go through this to write down why this boiling point is higher than this one and why this boiling point is higher than this one. Let's also play nomenclature because it's here. 1, 2, 3, 4, 5 carbons length, so pent. It's an alcohol, so anol. And then 1 because I always assign the lowest possible number when I count it up to the functional group, so OH on 1. For this next example, there's 1, 2, 3, 4 carbons in the chain, or if I went 1, 2, 3, 4, put it down here, but 4 carbons in the chain, longest chain, so I'm now going to call it, instead of pentanol, butanol, but for 4. The OH is on 1, so the butanol, 1 butanol. And this group is a methyl group. It's an extra carbon on there. So it's on carbon 3. Over here, same story, 1, 2, 3, 4. So but. It's an alcohol, so anol. And then 1, 2, 3, 4. This carbon right here, so on carbon 2. So 2-methyl 1-butanol, 3-methyl 1-butanol, and 1-pentanol. Okay. So from boiling point, it's going to go to melting point. So boiling points are significant, and actually they make a little more sense in that you can predict based on those 3 factors: the molecular mass, the strength of the molecular force, and the ability of the molecule to fold in a way or interact in a way that it can form that force with another molecule. So the intermolecular forces and the ability to interact, they're both going to impact the strength of intermolecular forces. Melting point, on the other hand, not as predictable. So I'm going to limit what I emphasize to things that have an interesting bio component. So we already mentioned saturated, unsaturated fats, and that's what's coming with this. So the melting point is the highest temperature in which the solid can still be seen, because once you go above the melting point, the solid now turns into a liquid. So again, we're changing our perspective of what the melting point and boiling point are. I'm using a practical lab-based definition as opposed to a formal definition based on a mathematical principle or I guess, defined concept in GChem certain way. I'm going to go with just the practical. If it's above the boiling point, it's a gas. Below the boiling point, it's a liquid or solid. If it's above the below the boiling or melting point, it's going to be a solid. Above the melting point, it's a liquid or a gas. So combining those 2 thoughts, if it's lower than the melting point, solid; above the boiling point, liquid or gas, excuse me; in between the melting point and the boiling point, a liquid. Okay, intermolecular forces play a role in determining the melting point. The mass doesn't really play that big a role, and packing plays a bigger role in melting than it does in boiling, meaning how they come together, because they're in constant contact and they're not coming together, leaving. Intermolecular interactions become much more significant. So generally speaking, if it can pack tighter, if the molecules can get closer together, they will have an increase in melting point. Stronger forces require higher energy to move things away from one another. The example did earlier dealt with fats. Really, really good example. So higher molecular mass isn't a case of the molecule being lifted up. This is no longer kinetic energy, 1/2 mv squared. This is higher mass simply means longer chain. The longer the chain, so this carbon is carbon chain is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Even number, so a naturally occurring fat built from 2 carbons at a time. Melting point of 45. If I make it a little bit longer, so this one is, again, it goes up by 28. So I added, that meant 2 carbons, because it has to be an even number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Notice it went up ever so slightly. And then if I increase it a little bit more, again, was it by 28. So now this was 12 carbons, 14 carbons is by 16. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Went up by about another 10 degrees or so, not exactly 10. And then finally, stearic acid. So we're following the trend: 12 carbons, 14 carbons, 16 carbons, 18 carbons. And the mass goes up again by 28. The melting point goes up, well, not quite 10. So 10, 8, 6. The trend again is not perfect, but it has to do with the longer the chain, the more it can tie knots. So if you have short strings, you can't really thread them together as well as long strings will knot themselves up more readily. Okay, so length of chain, longer the chain, the easier it is to interact. Also, notice everything is flexible. Everything is sp3 hybridized. So again, these represent no pi bonds anywhere, no double bonds. So everything's sigma bonds, and therefore you can rotate around a sigma bond. Pi bonds, because of the nature of the p orbitals, they can't rotate around because you'll break the bond. Those make it more rigid. So we have a second packing factor. And that is how the double bond plays a role. Okay, so I'm going to start with stearic acid, which again was the 18 carbon species. I'm going to compare it to something called oleic acid, oleanoic acid, and a few others along the way. But oleic acid, let me just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12, 13, 14, 15, 16, 17, 18. So 18 carbons. It has 2 less H's. So molecular weight is essentially the same. The length of chain, essentially the same, but notice the melting point is way different. So just to make sure I understand this, let's say 25 degrees is standard temperature, this will be a solid. This will actually be a liquid. Lake acid is liquid. When you have a double bond, again, you don't have as much flexibility. So when the molecule becomes inflexible, it cannot tie knots around another molecule, can't interact as well with another molecule. So when you have a saturated fat, you get stronger intermolecular forces between neighboring stearic acids. When you have unsaturated, you do not pack as well. So saturated packs well. Unsaturated doesn't pack well. Which means if it doesn't pack well, the boiling point, weaker forces, melting point, excuse me, can be lower. Let's see if the trend continues. So linoleic acid, this compound, linoleic acid, is still 18 carbons, but now it has 2 double bonds. So it has even less flexibility. So it is more rigid, it won't pack together as well. So flexible molecules have strong interactions, they pack well, melting points higher, more pi bonds, less and less. And finally, linoleic acid, even lower. But now it becomes diminishing returns. 1 pi bond significant, another pi bond still noticeable, and then 3 or more, it starts to be just a moot point. All it does about the same thing. So fun random fact, I don't know if this is that fun or not, but if you compare Arctic fish compared to warm water fish, just a cool little study they do, because the temperature that Arctic fish are swimming in, that water is close to freezing, close to zero. And because they swim in that, if they have fats of this nature, it'd be a solid. Whereas if this was in a room temperature, or let's say a fish that swims in water at 25 degrees, it would be a liquid. So if you need your cell membranes to be liquid-like, more fluid, ability to change shape and be more mobile, then at a very high temperature, everything's going to be liquid. So you don't need unsaturated as much. So you could do a mixture of stearic acid and linoleic acid to get some sort of compromise and have a melting point, I don't know, close to water and still have it behave like a liquid. But if they live in icy conditions to make their cells not freeze up, they actually have to incorporate more and more pi bonds. So if you've ever been told that Arctic salmon, Arctic fish are some of the best to eat, it is because their fats have a lot more pi bonds. They're a lot more unsaturated. They're a lot healthier for us. They're not trans fats that have been turned or hydrogenated into something else. They're more of these, I don't know, healthier fats, the ones that are liquid. Just random fun fact. Okay. Want to look at this? The same sort of example we did before. We did lake acid, which has the double bond like this. This double bond, and again, it's inflexible, but when they are across from one another, or on the same side. So this sigma bond is below it, sigma bond below it. This one's below it, but then now above it. For whatever reason, when they're in the trans position, and what we mean by that, across the double bond, one is below the double bond, one is above the double bond. Here, they're both below the double bond, or on the same side of the double bond. So I want to put that word in here. This is called a trans double bond. This is called a cis. The word trans fat has absolutely nothing to do with the trans orientation of it. So just coincidental, they use the same word. But trans fats and cis fats. I'm going to use those terms completely incorrectly if you're a bio person or if you're a nutrition person. But trans orientation double bond and cis orientation double bond, the cis disrupts the structure more, it can't pack as well, the melting point goes way down. When it has this, it still goes down from not having, like unsaturated, having a pi bond is going to make it less flexible, so it's not going to pack as well, so melting point will go down, but not as much if it's cis. And just compare that to stearic acid, which has no pi bond. So if you have a pi bond that's trans, it goes down a little bit. If you have a pi bond that's cis, it goes down a lot. So the healthiest acids or fatty acids are the ones that have cis bonds. Okay, so the type of unsaturation plays a role. And again, unsaturation means it has a pi bond. And you can remember this by saying saturated with hydrogens. If you have a double bond, that's one less H here, one less H here. So it's not saturated. You don't have the maximum number of hydrogens on the compound. Okay. Cis compared to trans, those bonds. Lots of information. This is practical applications of OCHEM, a very fun part of the class that we will do early on. And hopefully it'll be grenade learning for you as well, where you'll cover it in this class, you'll think about it, it'll be on your palette, if you will, but it won't be till you apply it in the future in whatever path you go. If it has any bio component, you're going to have to know a lot of what we just talked about. And when it makes sense in that situation, that alarm is going to go off and yeah, this worked. So that said, we have completed yet another Toddcast. So once again, thank you, and I will see you in the next one. Until then, bye.